A very good morning to all of you. Today we would see what is simple harmonic motion, what are its basic properties. At the end of this presentation, you should be able to understand systems that oscillate with simple harmonic motion. When I say simple harmonic motion, the term which strikes your mind should be its harmonicity, its periodicity, the term oscillation. Two pictures I have given. One is of that of a monkey swinging on a tree branch and another a baby in a swing. We can see that these two motions, we can call them as oscillations. How do we say so? As the baby, for example, you can take this second picture. As the baby goes up, the springy rope pulls her down. And as she comes down, the rope takes her up. Thus, it is a periodic motion, a harmonic motion. Now, in this presentation, what are we going to see? We would see what is simple harmonic motion, the basic definition, the equation and properties, and when we have the combination of simple harmonic motion along the same direction, how it could be, when they are perpendicular to each other, how they would be, and what would be the beautiful application of it, the Lissajous figures, and then the frequently asked questions in this presentation. When do you call a motion to be simple harmonic? The basic one-line definition is that when the acceleration is directly proportional to its displacement from a fixed point, the point which we call as equilibrium position, and when the acceleration is always towards that point, you call that a simple harmonic motion. Now, what is this equilibrium position and what is this acceleration towards it? How do we visualize this? Consider these marbles rolling on the spherical bowl. What happens? A marble that is free to roll inside the spherical bowl, it has an equilibrium position at the bottom of the bowl, where it will rest with no net force on it. Now, if pushed away from equilibrium, the marble's weight leads to a net force towards the equilibrium position, and this force is the restoring force. Now, when the marble is released from the side, it does not stop at the bottom of the bowl. It rolls up and down each side of this bowl, moving through the equilibrium position, and this repetitive motion is called oscillation. Any oscillation is characterized by a period and frequency. This could be visualized as a projection of a uniform circular motion onto one axis. The best practical applications of simple harmonic motion are the undamped simple pendulum and the undamped spring mass system. Some other common examples could be the vibrating tuning fork, the weight on the spring, and the boy on the swing. Now, when I say periodic motion, I am going to have an oscillation, and the time to complete one full cycle is called the period of the oscillation. And the number of such cycles per second is called the frequency of the oscillation. Now, how do we derive the equation of motion for a simple harmonic case? We know that simple harmonic motion is a motion in which the restoring force is directly proportional to the displacement from the mean position and is directed towards the mean position. Now consider the best example of the spring mass system. A block is attached to a spring on a frictionless table. Now, the spring gives a restoring force to the system and it is equal to minus kx, where k is the spring constant. Now, From Newton's second law, we know force is equal to mass into acceleration, where m is the mass of the particle and a is the acceleration. Now we can equate these two forces, and as I equate, I go for representing the acceleration as the time rate of change of velocity, which is nothing but equal to d square x by dt square. So when we equate these two forces, one is from the restoring force relation F is equal to minus kx and F is equal to ma from Newton's law, I end up in an equation as m into d square x by dt square is equal to minus kx. And as I bring the m to the other side, it takes up this form as d square x by dt square plus a constant omega square x equal to 0, where this constant omega is equal to root of k by m. Now this equation is called the equation of the spring mass system, the simple harmonic motion. It is a second order differential equation. Now, what could be the solution of this equation? The best possible solution could be a cosine solution. X is equal to a cos omega t. So you can very well see that as you take the first derivative of it with respect to time, you end up with minus a sine omega t. Now further, as you take the second derivative, you end up with again minus a cos omega t. So when we add this with omega square x in the equation, we end up that x is equal to a cos omega t is indeed a solution. Thus, d square x by dt square plus omega square x equal to 0 is the simple harmonic motion equation. So, any simple harmonic motion could be represented with the solution of the form x is equal to a cos omega t. Its velocity takes up the form minus omega a sine omega t, and the acceleration takes up the form minus omega square a cos omega t. And these three could be depicted in the picture with the pink, green and red graphs. Now a quick check of what we have learned till now. If I am asking you a question on what is the frequency when a mass oscillates on a horizontal spring with period t is equal to 2 seconds. So we should be immediately able to say that the frequency is inversely proportional or equal to t. So f is equal to 1 by t. So the answer should be 0.5 Hertz. Now, what is the resultant of the combination of two simple harmonic motions? So this is the next bite which we are going to chew here. In the sense, we have seen the basic property, the equation of simple harmonic case, and now we are going to see the combination. So when we have two simple harmonic motions along the same direction, represented by these two equations, y1 is equal to a1 sine omega t plus alpha 1, y2 is equal to a2 sine omega t plus alpha 2, the resultant is going to be a linear addition of these two, that is a1 sine of omega t plus alpha 1 plus a2 sine of omega t plus alpha 2. Now as we expand sine of a plus b, we end up with say that sine a cos b plus cos a sine b, and as we do the expansion, we get a resultant expression as capital Y is equal to capital A sine omega t plus phi, where capital A is equal to a1 square plus a2 square plus 2 a1 a2 cos of a1 minus a2, and tan phi, which is nothing but a1 sin alpha 1 plus a2 sin alpha 2 divided by a1 cos alpha 1 plus a2 cos alpha 2. So we can see that the resultant is also in the same form as that of a simple harmonic solution. It is a simple harmonic case. Now when we have two simple harmonic motions with equal periods at right angles to each other, what could be the equation be? The resultant is, when we have a sin omega t plus alpha and y is equal to b sin omega t, when we have the combination of these two, one is at right angles to the other. When one alpha is 90 degrees and another is at 0. In the sense both are at right angles to each other, the resultant is an equation of ellipse. So which is x square by a square plus y square by b square minus 2xy by ab cos alpha equal to sin square alpha. That is, when two simple harmonic motions, when they are in phase with each other, that is, when the alpha is 0 or pi, then as we substitute the value of alpha with pi, cos, sin pi, cos pi, when we substitute the values, we end up with a simple straight line equation as y is equal to plus or minus b by a x, and this is depicted in these two pictures. Now in case 2, when alpha is equal to 0 or alpha is equal to pi by 2, the two simple harmonic motions are out of phase with each other, and as we substitute the value for cos 0 and cos pi by 2 or sin 0 and sin pi by 2, we end up with an equation with x square by a square plus y square by b square equal to 0, which is nothing but the circular motion case. Now when the two simple harmonic motions are out of phase with each other by 90 degree and their amplitudes A and B are equal, it is a circular motion. Whereas when they take up different ratios, that is A is equal to 1 and B is equal to 2, or A is equal to 3, B is equal to 2, or A is equal to 3, B is equal to 4, the ratios vary and we end up with the different patterns of Lissajous figures, which we do in our laboratory. And this is a cathode ray oscilloscope which has produced the combination of two simple harmonic motions, and we have got the Lissajous pattern. This we would be doing in our regular laboratory session, and this is the theory behind it. So you can see this. So the construction of Lissajous figures is so beautiful that as we combine two simple harmonic motions, we end up with different patterns at different values of alpha. So the frequently asked questions, what could be a definition of a simple harmonic motion? What are Lissajous figures? When do you get a circular pattern? When do you get a straight line? How are they produced? How do you call a force that makes a particle move along a circle? And you can also expect a simple problem of this type. A clown is rocking on a rocking chair in the dark. His glowing red nose moves back and forth a distance of 0.2 meter, exactly 30 times a minute in a simple harmonic motion. What is the amplitude? What is the period? What is the frequency? All these things could be asked. So hope we have understood what is simple harmonic motion, what is the combination of it, when can you expect the different pattern of Lissajous figures, and when will we able to say that we get a straight line, a circular motion, or the different patterns of it depending upon the ratio of